Okay, here we go with the second part of thermodynamics. So if you were on for the Zoom episode there, I did tell you what the graph should have looked like. And the graph of what I was talking about was a graph of temperature versus heat of the ice cube. So what we did was you put an ice cube on a hot plate and you added heat to that ice cube. And as you added heat, what happened to the temperature? And for the most part, what happened was, if you're starting off with ice, we need to start off at a negative temperature. So we had let's say, negative 25 degrees. And this is going to be measured in Celsius. But we are going to be below zero. So this would be my zero mark. And what happens is, if I add heat to this ice, the temperature is going to rise. And it rises until it reaches zero. Once it hits zero, this is the part that we're going to be talking about today. This part is the amount of energy needed to complete a phase change. So all in all, what this is going to look like is something like this. Okay? And as we're looking at this, we're going to see that this is in the stage of solid. This is in the phase of liquid. And this would be in the gas form. And if we're talking about water, or H2O, this would be ice, water, and steam. All right, we all good? So why the difference? Anybody want to take a stab at that? Well, a couple of things. There's going to be an amount of energy needed to complete a phase change, because chemically what you would need to do is you need to break down the bonds that make it a solid. And there's also going to be, if you notice, a different slope on these lines here. And what that slope is going to correspond to is the specific heat of that object. So what does that mean? That means the specific heat of water is different than the specific heat of ice. Everybody got that? All right, gravy. So what are we missing here on the graph? Well, we're missing that when we get to 100 degrees Celsius, what's going to happen here is an amount of energy is needed to complete that phase change of going from water to steam or liquid to gas. So what are we looking at? We need to find out what we had previously was that Q was equal to MC delta T. That requires a temperature difference. If we're going to be going from solid to liquid, or this phase change here, that is a zero temperature difference. So I'm not going to be using this because that would mean that I have zero amount of energy. Well, that's nuts. So what I'm going to be looking at here is the amount of energy needed to complete a phase change is going to be dependent upon the mass and the constant of the heat of either fusion or vaporization. And those are the two that we're going to use. So that means that we're going to need some constants now, right? Okay, so real quick, what I'm looking at here is, if I want to find out how much energy, let's go for a minimum, okay? What is the minimum heat needed to melt, let's say 1 kilogram of ice? Okay, so the minimum amount to melt would be, I need to go from ice to water. So if I'm starting at zero, I'm going to go from here to here. How much energy is needed to do that? This would be the stage of fusion, and then this would be the stage of vaporization. So if I'm looking for the amount of energy needed to go from here to here, I'm going to see that the heat of fusion would be the mass times the constant of heat of fusion. So we're going to need to know what that heat of fusion is. And if you want, I can give you the heats of fusion here. And I'm also going to give you some other useful information, which is going to be handy. And if you want, you can write these down. What we're looking at here is for water. The heat of fusion is a very large number. Heat of vaporization, an even larger number. Okay? Does that make sense? Sure. How does that make sense? Well, if I'm going to be going from water to vapor, it takes a lot more energy than it does to go from an ice cube to water. And vice versa if I want to take energy away. These are the specific heats of ice, water, and steam. Notice that they are different. And they should be different. So what can you grasp out of this? You could say that the specific heat of water, or the amount of energy to change the temperature of water, is much higher than that of ice. So what is it easiest to change the temperature of? That would be steam. Okay, keep those in mind, because we're going to use those in a second. Okay, so if I want to find out the minimum amount of heat needed to melt the 1 kilogram of ice, I'm going to have 1 kilogram of ice times the heat of fusion, and the heat of fusion, 3.35 times 10 to the 5, and that would be joules per kilogram are my units. And of course, I made this one nice and easy so you can see the concept. So kilograms cancel, and I will see that the heat of fusion is 3.35 times 10 to the 5 joules. Or I could say 335 kilojoules. That's a lot of energy. Or it's really not that much because a joule is a very small unit, right? Okay, gravy. Moving on. This should be a little bit familiar from last year, so I'm going to speed through this a little bit quicker. And I'll leave the graph up. I'll leave that as much as you can see, and then we'll write the problem down here. Okay, so I want to find out, question 2, how much heat is needed to change the temperature of H2O from, let's say, negative 12 degrees Celsius to 125 degrees Celsius. A couple of things you got to keep in mind here, right? Like what? What do you got to keep in mind? Godzilla, you know, right? Nah, I'm not going to do that again. Okay. A couple of things you got to keep in mind here is that we're going to be going from here to here to here to here and all the way up into steam. So we got a lot of heats to require here. So what I'm going to label this as is, first off, I want to find out how much energy is required to go from negative 12 degrees Celsius to 0 degrees Celsius. And I'll call that Q1. Maybe I'll do that over here. That'll be Q1. Are we still in the line there? Yeah, we're still good. Okay. All right. Q2 would be the amount of energy needed to complete the phase change here. And, oh, what's missing here? Well, let's say that we have water. So let's say that the mass of this H2O is going to be, oh, I don't know, 750 grams. Okay. So the next thing is we want to find out how much heat is needed to complete the fusion, or going from ice to water. Next, Q3 would be how much heat is needed to go from 0 degrees Celsius to 100 degrees Celsius. Q4, how much heat is needed for vaporization? Meaning, how much heat is needed to go from here to here to complete that phase change. And then Q5 is going to be the amount of heat needed to go from 100 degrees to 125 degrees. And then the total amount of heat would be my total answer. How much heat is needed to change the temperature of water of 750 grams from -12, so somewhere around here, all the way through here, through there, through there, through there, through there, all the way up to 125 degrees. So let's find out what all these things are. Well, I'll start off with Q1. Q1, I'm going to ask myself, does it require a temperature difference? Yes, it does. So I'm going to use MC delta T. Q2, does that require a temperature difference? It does not. So that would be M times the heat of fusion. How about Q3, from here to here? That has a temperature difference. So that would be MC delta T. Q4 is going to be from here to here. No temperature difference. So that would be M times heat of vaporization. And then this does have a temperature difference, MC delta T. All right, let's put this out of the way now. Move this up a little bit so you can see it better. All right, so one more key aspect here is, it's not necessarily throwing a curveball here, but what I'm looking at here is this C. Well, what C am I talking about? The C is going to correspond to the specific heat of the material. So I'm going to see that the specific heat is going to be different every time, because for ice, I'm going to use a specific heat of ice, specific heat of water, specific heat of steam. Okay, so let's plug and chug here. C is going to be a specific heat of ice. This C will be for water, and then this C will be for steam. So here we go. The mass is going to be 0.75 kilograms, because that's going to be for all the masses. Specific heat of ice. Well, the specific heat of ice was 2090 joules per kilogram degrees Celsius. Change in temperature. Now, the change in temperature that I'm going to be using here is the -12 to 0, which would be a change in temperature of 12 degrees Celsius. Q2 would be the mass, 0.75 kilograms, times the heat of fusion of ice, which we said was 3.35 times 10 to the 5 joules per kilogram. Q3, the amount of heat needed to go from 0 to 100 would be the mass, 0.75 kilograms again. Specific heat of water, be careful there, 4186 joules per kilogram degrees Celsius. Temperature difference. So what temperature difference are we talking about here? We're talking about 0 to 100. So that would be 100 degrees Celsius. 0.75 kigs again. Heat of vaporization. Heat of vaporization is 2.26 times 10 to the 6 joules per kigs. And then this guy here is going to be, again, the same mass times the specific heat of steam. And the specific heat of steam is 2010 joules per kilogram degrees Celsius. And the temperature difference is going to be from 100 to 125. That would be 25 degrees Celsius. Okay, so let's find out what they are. So here we go. Q1, Q2, Q3, Q4, Q5. Take out my handy dandy calculator here. Let's make sure we're all on the same page here. Q1 will be 0.75 times 2090 plus, how about I turn my calculator on? Yeah, that'd be good. 0.75 times 2090 times 12 would be 18,810 joules. Q2, 0.75 times 3.35 times 10 to the 5 is 200. Hey, what happened there? 251,250 joules. 3.75 times 4186 times 100 is 313,950 joules. Q4, we're getting there. 0.75 times 2.26 e to the 6th. I've got 1,695,000 joules. Whew. 251,000, 1 million. That's a lot. And Q5, last but not least, I got 0.75 times 2010 times 25. Of course, we get a decimal. Mamma mia. 37,687.5 joules. And what I'm going to do is I'm looking for the total amount of heat needed. So I'm going to add all these bad boys together. 695 dippy dippy doo plus 313 950 251 250 18,810 plus, oh, I got them all. 1, 2, 3, 4, 5. Yes, those are all 5. Okay. Let's get rid of that. We got 2, 3, 1, 6, 6, 9, 7.5. Skadoop, skadoop. And I have joules here. So that means I have 23, let's say 17 kilojoules. Agreed? 2,317 kilojoules of energy are needed to take an ice cube and go from negative 12 degrees Celsius to 125 degrees Celsius. Oh, I moved the calculator out so you can see it. Okay. Oh, I don't know why I'm pausing. You can pause this anytime you want, right? Yeah. Okay. What am I waiting for? All right. Last but not least, what we're going to do is I'm going to challenge you now on this one. And what you're going to need is the same thing you have written down already. That's these bad boys right here. Okay. And what we're going to do now is, let me see what I did with it now. Oh, 175.3. All right. Okay. So we're now going to take an ice cube, and what we're going to do is we are going to add a certain amount of heat. But let's say that the temperature of the ice cube, we need to start out at a certain temperature. Well, I keep losing this. 15, negative 25. All right. We're going to say the ice cube is going to have a mass of 250 grams. And it starts out at a temperature of negative 25 degrees Celsius. And we're going to add an amount of heat. And the amount of heat that we're going to add is 175.3 kilojoules. So we're going to add 175.3 kilojoules. What do you think's coming next? What do you think's coming next? Huh? We have ice at an initial temperature, negative 25 degrees. And we're going to add heat to it. So it's kind of obvious what we're looking for next, right? Do you want us to find... Oh, well, let me take a look at this. Do you want us to find how many joules that's equivalent to? Obviously not, you bonehead. That would be too easy. That would be like, you know, Macapin type stuff. Obviously, we're looking for probably what's the final temperature going to be, right? Right? Yes, I think so. Okay. Yeah. You're right. You're both right. Actually, only one of you are right. We are looking for the final temperature. What is the final temperature going to be after we add all that heat? But we're also going to be admitting the fact that, yes, kilojoules are something that should have been Macapin a long time ago. All right? So what are we going to need to do here? Well, the first thing that we're going to need to do is, if I had that graph, I'm going to be starting at negative 25. I go to 0. I go up, I go to 100, and I go up again, okay? I will call that Q1, Q2, Q3, Q4, and Q5. And our mass is 250 grams, so our mass is going to be 0.25 kilograms. 0.25 kilograms. So we're good there, okay? So what I want to find out is I have 175.3 kilojoules of energy in my tank. 175,300 joules. Okay, so the first thing I want to find out is Q1. Well, how much energy is required to go from here to here? And then I'm going to ask myself, do I have enough to do it? Q1, I have a temperature difference. I'm going from negative 25 degrees to 0, and up here is 100 if necessary. So Q1, let's find out that bad boy first. MC delta T. And this is going to be the specific heat of ice. So Q1 is going to be my mass of 0.25 kilograms times the specific heat of ice. And I look up here, specific heat of ice, 2090 kilograms. No, kilograms. What are you doing? Joules per kilogram degrees Celsius. Temperature difference, 25 degrees Celsius. All right, let's find out what that amount of energy is and if we have enough. All right, 0.25 times 2090 times 25. I have 13062.5 joules. Okay, so I ask myself, do I have enough? 13,000. I have 175,000. Yes, that's enough. So that means that I did have enough to get to here. Agreed? Okay. So if I have that much, let's find out how much Q2 is needed. How much heat is responsible for getting from here to here? Okay. Q2 is going to be my mass times the heat of fusion. So that would be 0.25 times the heat of fusion for water. And the heat of fusion is right there, 3.35. You can see that, right? Yeah. 3.35 times 10 to the 5th joules per kilogram. Skadoop, skadoop. Okay, so I'll take 0.25 times 3.35 e to the 5th. Okay, and that comes out to 83,750 joules. Okay, so do I have enough energy to get to there? Well, 83,750 plus 13,062.5. Whoa, easy now. 13,062.5, yeah. Gives me 96,000. Do I have 96,000? I most certainly do. But what I'm going to do is I'm going to take the 175,300 minus this total. And that means that I have 78,487.5 joules left over. Okay, I'm going to see what I can do with that. All right, so let's find out Q3. Q3 is from here to here. That would be a temperature difference. And that temperature difference requires me to use MC delta T. This would be the specific heat of water. So I have 0.25 kilograms times the specific heat of water. All right, so 0.25 times 4186 times 100 gives me 104,650 joules. Okay, when I add that to 78,487.5, I'm going to see that that goes up to 183,000 joules. Do I have enough? I do not. So that means I do not have enough to get to here. Okay, so what do I have left? Remember I wrote this here. I have this amount of energy left over, right? 78, or sorry, that was my, that was my leftover, right? So I have that much energy from here to raise the temperature. So what I'm gonna do is, since I know I'm gonna be left somewhere in here, I'm going to take that 78,487.5 joules and set that equal to MC of water times the actual temperature change that it's going to correspond to. So let's go ahead and do that. I'm going to see that I have 78,487.5 joules is equal to the same mass, 0.25 kilograms. Specific heat of water, 4186. It was 6, right? Not 7, right? 4186, yes. Joules per kilogram degrees Celsius times my temperature difference, which would be T final, is what I'm looking for, minus T initial, and the initial would be 0 degrees Celsius. So now from here, all I'm doing is just solving for what TF is, because if this is 0, that drops out, and it's minus 0, so it doesn't really make a difference. So I have the temperature final would be 78,487.5 joules divided by 0.25 kilograms times 4186 joules per kilogram degree Celsius. So here we go. 78,487.5 divided by 0.25 divided by 4186. I have a final temperature of 75 degrees Celsius. Okay, that's all good and fun. Let's see if it makes any sense. 75. Well, we said we're going to be somewhere between here, right? Is 75 between 0 and 100? You're darn tootin' it is. Absolutely. All right, guys, good job. What do you got to say about that? Well, I kind of understand it. About a degree of difficulty or level of confidence, I'll probably give it Maybe a 6. I told you so. In your faces. Okay, guys. Have a good one. Stay safe.